Known in the USA as gas metal arc welding, or GMAW, this process can be further distinguished in the MIG and MAG processes. The arc, surrounded by a protective gas, is struck between a consumable wire electrode and the work. The continuous consumable electrode wire is mechanically fed from a spool to a manually or mechanic motor-driven rollers of adjustable speed. The rate of burn-off of the electrode wire must be balanced by the rate of wire feed, with a control cable from the gun switch to the control contacts. Generally, wire diameters are quite small compared with other types of welding, ranging from 1 to 1.6 millimeters, although up to 3 millimeters or down to half a millimeter may be used occasionally. The high currents used in MIG and MAG welding, combined with the small diameter wire, result in very high melting rates, varying from about 40 millimeters a second up to 340 millimeters a second. In manual metal arc welding, metal is transferred in globules or droplets from the electrode to the work.
My drives.
Now, if the current is increased to the continuously fed gas shielded wire, the rate at which such droplets are projected across the arc increases, and they become smaller in volume, and the transfer is then in the form of a fine spray. With lower arc voltages, say 15 to 22 volts, and currents usually less than 200 amps, transfer takes place in globular form, but with intermittent short-circuiting of the arc. The wire feed rate must just exceed the burn-off rate, so that intermittent short-circuiting will occur. When the wire touches the pool and short-circuits the arc, there's a momentary rise of current which must be sufficient to make the wire tip molten. A neck is then formed in it due to magnetic pinch effect, and it melts off in the form of a droplet being sucked into the molten pool, aided by surface tension. The arc is then re-established, gradually reducing in length as the wire feed rate gains on the burn-off, until again short-circuiting occurs. In order to keep stable welding conditions with a low voltage arc, say 17 to 20 volts, which is being rapidly short-circuited, the power source must have the right characteristics. If the short-circuit current is low, the electrode will freeze to the plate when welding with low currents and voltages. However, if the short-circuit current is too high, a hole may be formed in the plate, or excessive spatter may occur due to scattering of the arc pool when the arc is re-established. In between the spray transfer and dip transfer ranges is an intermediate range, in which the frequency of droplet transfer is approaching that of spray, yet at the same time short-circuiting is taking place, but is of very short duration. This semi-short-circuiting arc has certain applications, as for example the automatic welding of medium thickness steel plate with CO2 as the shielding gas. This system allows all position welding at higher energy levels than short-circuit transfer. The power source provides two current levels: a steady background level, too low to produce spray transfer, and a pulsed peak current, which is superimposed on the background at regular intervals. The pulsed peak is well above the transition current, and usually one drop of metal is transferred during each pulse. The combination of two current levels produces a steady arc, with axial spray transfer at currents below those required for conventional spray arc welding. Argon is used as a shielding gas because it's chemically inert and forms no compounds. It's especially useful in welding non-ferrous metals and alloys. But in welding steel, it exhibits an uneven negative pole at the workpiece, the electrode being positive, to give an irregular weld profile. Argon plus 1 or 2% oxygen gives a higher arc temperature, and the oxygen acts as a wetting agent to the molten pool, making it more fluid and stabilizing the arc. Helium is sometimes added to mixed gases. Its presence increases the arc voltage and consequent heat input. Mixing it with argon, oxygen or CO2 controls the pool temperature, increases wetting, and stabilizes the arc. Carbon dioxide or CO2 has the advantage of being the cheapest shielding gas, and it can be used for welding both alloy and plain carbon steels, up to 0.4% carbon. There's some dissociation of CO2 in the arc, producing carbon monoxide and oxygen, and this requires the filler wire to be adequately deoxidized to prevent porosity. Some wires rely solely on manganese and silicon for this deoxidation. Others include the more efficient elements, aluminium, titanium and zirconium, in varying proportions. Generally, the arc is less smooth with CO2 than with argon CO2 and argon oxygen. The arc conditions are more critical, and there's more spatter.